excited to present my presentation, which is called Two-Stage Recommendation System at Unity. So a couple words about me. My name is Denis Vorotyntsev. I work as Senior Data Scientist at Unity. I work in the candidate selection team. I added a link to my LinkedIn page, so in case you want to reach me out. So my presentation will consist of 3 parts. I will briefly describe the Unity ads and the motivation behind 2 stages in this recommendation system. Then I will share some technical details and the struggles we faced. And then I will briefly describe the workflow that we apply when building models and creating some new solutions. So let's start. The Unity ads is a middleman between publishers and advertisers. So publishers are game creators who create new games and they want to make money by doing it. So they place ads in their games and to be paid. Advertisers, on the other hand, want to bring new audience, new gamers into their games, and Unity ads connects these 2 parties together. So we are ensuring that publishers will get a lot of use, a lot of money by publishing ads. Advertisers will get the most relevant audience they're looking for, and the gamers can get the most personalized games, the most personalized ads as possible. So let's look at the example of such ad. This actual screenshots from the game. So you're playing, you're driving the car, suddenly your car explodes and you are sent to the game over screen, where in exchange to local currency, exchange in-game currency, you can watch an ad. If you click this button, you will be transferred to the next screen with the video of an ad. And it's up to you now if you want to download this game or continue playing your game. So when gamer clicks a button, we receive an ad request, and that request consists of user features such as platform, country, user profile, which consists of information about user preferences, his previous games, his previous interaction with other ads, and other features. We collect a list of available campaigns that we can show to a given user based on the user features, for example, platform or country. Our goal is to select the most promising campaign to show to a user. And we are doing it by predicting the probability of user installing the game after seeing an ad, and to multiply this probability by the cost of the campaign and select the campaign with maximum cost, with maximum expected value. For predicting conversion, we're using conversion prediction model. So we send user features and campaign features through a conversion model. In this model, which is represented by a bunch of fully connected layers, what is happening is that we receive features, we preprocess them somehow, then we repeat user features as many times as we have campaigns, and send this input to the model. Model makes predictions for every such interaction and return the probability of installing each campaign. Then this probability multiplied by the cost of the campaign, and the campaign with highest expected value is selected. So we send the campaign and the bid to the auction, and if we win an auction, the campaign is shown to a user. So this setup is running on the GPU, so all our models are deep learning models, and we have a very high load. So we have 2.2 billion devices globally, and approximately 60K requests every second. And some time ago, we noticed that the number of input campaigns is actually growing. And it is a very good situation for the company, because more campaigns means more money and more diverse games for a user. So it's always a good thing to have more campaigns. But from technical perspective, it's not a very good situation to be in, because more campaigns means larger input to the conversion prediction model, which means that we need more machines to do our serving, and the latency, so we cannot make predictions as fast as before, and latency is increasing as well. And the problem is that we have a hard limitation on latency, and we have a hard limitation on the amount of GPUs we can use for serving. And at some point, if this trend continues, we can get to the point where we cannot continue doing serving. So we decided to do something about it. And we want to reduce costs of serving. We want to reduce the amount of GPU that we use for doing the serving and decrease latency. And our solution should produce, in the best case scenario, should produce exactly same system as before, but with reduced latency and costs. So we should have the same selected campaigns, same statistics as before. And we have 2 possible ways to solve this problem. First one is to affect the conversion prediction model. So we can came up with new better architecture, we can apply pruning, node isolation, and all other fancy techniques, but we decided that it will affect system too much. So we decided to focus on the affecting the input to the conversion prediction model, which is common nowadays in the recommendation system. So we decided to use a prefiltering model to select campaigns which will be sent for the final evaluation. So the diagram changes. We receive an add request with the campaigns, and instead of sending it right away to the conversion prediction model, we send this input to the candidate selection model. And the goal of the candidate selection model is to select the most promising candidates, which will be sent to the conversion model. So here we select campaigns 2 and 4, which are then sent for final evaluation to the conversion model. So this candidate selection model, it is the same conversion prediction model, but with slightly better architecture. It predicts the probability of game being installed, then this probability is multiplied by the price of the campaign, and then we select top K campaigns which sent to the model. And this top K is lower than the total number of campaigns which is sent to the candidate selection model. So let's say we sent for final evaluation 100 campaigns. We set top K to 10, which means that we reduce number of computations that we need to perform by 10x. If the candidate selection model is fast enough, if it doesn't consume GPU resources, this solution would work. So for candidate selection model, we decided to use state-of-the-art model in this area. At least it's been when we started this project. It's called 2 towers model. So the 2 towers model consists of 2 towers, user tower and campaign tower. We take user features and put it through user tower, campaign features through campaign tower. The output of the last layer of each tower is treated as user or campaign embeddings. We calculate the dot product between these 2 embeddings and take a sigmoid on top of that. And the output is treated as a probability of installing again. So the benefits of this model are that campaign features are static, so they don't change from request to request, and we can cache the embedding, so we don't need to recalculate it on every request. The second good thing is that we need to calculate user embedding only once, so we don't need to repeat user features as many times as campaigns. Also, the dot product is a relatively cheap operation compared to matrix multiplication we have in the deep learning models. So all in all, this model, due to the significantly fewer number of computations, can be run on the CPU. So thus, we are reducing consumption of the GPU resources. And this model works pretty well. But the question is how to measure the goodness of the model, of this particular model. So first premise is that running online experiment, running an A/B test is much more expensive than running offline experiment. So when running offline experiment, we can play with hyperparameters, architecture choices, etc., and we can run tens of experiments every day. It's not possible for online experiments. So we need to come up with some reliable metric which correlates pretty well with the outcome of online experiment. And we notice that, unfortunately, metrics that we calculate during model training, such as binary cross entropy, they do not correlate pretty well with the results of online experiment. And we decided to apply the following two metrics, to calculate following two metrics, recall and realized expected value. So the setup looks like following. We take a request and put it through a conversion prediction model and candidate selection model. Both models return probability of ad being installed, and we multiply this probability by the cost of the campaign and sort output list by this expected value, this multiplication. So right part of the screen, upper, so this thing here, the expected value of campaign 2 is $100, campaign 1 $90. The output of candidate selection model, it has same campaigns but different orders. So top 1 campaign is campaign number 3, then 5, etc. So we calculate two metrics. First one is recall, where we just check if the top campaign, campaign number 2 in this case, is within top K. Let's say that we calculate, let's say that top K is equal to 2. So recall at 2 is equal to 0 because these first two campaigns, they do not contain campaign number 2. Recall at 3 is equal to 1 because top 3 contain campaign number 2. So if we send top K these three campaigns, campaign number 2 would be selected, which is a good outcome for us. The problem, however, is that this metric, it affects, it punishes us too much for not selecting the best campaign. But the difference between top 1 campaign and top 2 or even top 3 campaign is not that big. So instead of using this metric standalone, we decided to calculate realized expected value. Here we just calculate how much value we are losing by applying prefiltering. So let's say we're calculating realized expected value at 2. So we select top 2 campaigns, 3 and 5, and check what campaign would be selected by the conversion prediction model. So in this case, campaign 3 would be selected. The price of the campaign is equal to $10, but the maximum amount, if there was no filtering, is $100. So realized expected value is $10 divided by $100, which is 10%. So we repeat these calculations for many requests and aggregate results to calculate this metric. And we notice that the results that this metric is more trustful than the metrics that we calculate during model training. Then when we look at our metrics during offline tests, we run an A/B test and we look at the same metrics that are commonly used in the A/B test in the company. So we look at number of starts, click, installs, conversion rates, total number of spends, etc., etc. So we, as I mentioned before, the premise of this model is that it should not affect the system, generally speaking. So we are trying to have either the same metrics, which in A/B test is not possible, of course, or metrics as close as possible to the situation in which we don't have a candidate selection. How we're doing that? For a small percentage of traffic, we do not apply a candidate selection model, so all campaigns are sent for evaluation to the conversion model. And by doing this, we can avoid having any biases or feedback loops in our data because we're using this data for training our models. And also we can run a negative test, which I will describe later. So let's jump to some technical details. So when we started this project, we used exactly the same data and the same targets, both for training conversion model and candidate selection model. But the problem is that the candidate selection model is not that powerful compared to the conversion model because of the lack of explicit and implicit feature interaction between these two models. So basic features are separated, and it's hard to incorporate a lot of knowledge into embeddings. So model is not that accurate. And also, the best possible predictions that we can have in the candidate selection model, realistically, are predictions which are exactly equal to the predictions of the conversion model. So we decided that it's a good spot for applying teacher-student approach, and we generate data, we load this data on machine, load the most recent conversion prediction model, and apply this model to the generated data to generate predictions using this model and use it as a target for candidate selection model. So we do it when training model during pre-processing step. So we noticed that this setup, it improved our metrics during offline test. We ran on the experiment, metrics were better as well. We noticed that the model converged much faster, so it's a good situation to have. However, this setup has one big problem, is that this training is much slower, and time plays an important role in our pipeline. So what we decided to do, as I mentioned, we have a small percentage of traffic which is not affected by the candidate selection model. So for this small percentage of traffic, in some, again, small percentage of cases, we save all predictions made by this conversion model during actual inference. And we use this log instead of making predictions during training. So it worked much better. So the training became much faster. And also we utilized some benefits by having this new input, new targets. The next thing is stateful training. So as I mentioned, time plays an important role in our pipeline. The question why? So the reason is that new campaigns, new ads are added to our system constantly. And the longer data generation and model training, the larger the delay between data appearing in our database and data incorporated as a knowledge to the model. So let's say new campaign is added to our system. Model training data generation takes, let's say, 1 day. That means that we have no idea how this model performs until until the new model arrives in our production. And some models can work in these settings. So for conversion prediction model, it's still a problem, but it's not that big of a deal, right? So we can use other information. Let's say we can use information on game ID, game embeddings to deal with it, and so on. So we still can make predictions, even if the training time is large. But for prefiltering model, it becomes a huge problem because when we predict conversion on the conversion side, we still predict something, right? But in the candidate selection, in the pre-filtering step, if the campaign is filtered out, we cannot show it to the conversion model, and it can create a very nasty feedback loop. So it's a good idea to avoid it and to make training as fast as possible. And to do that, we utilized this approach of stateful training. So let's start by describing stateless training first. In the stateless training, what is happening is that on every, so let's say we retrain model every 2 hours. So on every step, we generate data, we train the model, let's say we use last 7 days of data. The next step, again, we're using last 7 days of data, but now this data is shifted by 2 hours here, and so on and so forth. So stateful training, on the other hand, consists of 2 pipelines running at the same time. First one, exactly the same stateless training as I described earlier. But second pipeline is so-called stateful training. So in this training, instead of using last 7 days of data, we are using the most recent 2 hours of data. And instead of starting with random initialization, we are starting from pre-trained weights from previous iterations. So for example, here, if the model has been trained, has finished its training here, we're using the weights from the previous model. Here, we're using weights from this model, etc., etc. So this stateful training, in some sense, can be treated as fine-tuning using the most recent data. And well, actually, it is fine-tuning. And let's say that we generate data using last 7 days. In stateful training, we use last 2 hours of data. That means that amount of data that we use for training models is reduced by approximately 80 times. And thus, the time which is needed for generating data and time which is needed for training the model is also reduced by approximately the same magnitude. And it is extremely good achievement. So we dramatically reduced time which is needed for training the model, and at the same time we improved our metrics because of 2 things. First one is that we were fine-tuning our models instead of retraining them from scratch. Second, that we reduced the delay between data appearing in database and data incorporated into the knowledge of the model. So yeah, now the last but not least part, I decided to share some insights on how we organize our work and development workflow. So everything starts with an idea. We start with motivation of this idea. We came up with these ideas either from our own heads, research papers, or from our business partners. We export the data and define what needs to be done, and so on and so forth. In most of the cases, we don't need to build sophisticated models. Sometimes analysis is enough or some small tweaks, but let's discuss the more generalized approach. So let's say that we need to build a model. We start with experiments. Experiments are split into 2 parts. First one is local experiments, where we just binary check if model training works as expected. So we just check binary work or doesn't. The next step is training in the Kubeflow. So we're using Kubeflow because we have a lot of teams and limited amount of resources. So we need to organize training and make a queue so everyone has a chance to train their models. Also, Kubeflow allows us to make our research reproducible by utilizing Docker. So the Docker contains all the code necessary for training the model, and all steps are described in the config files. So we are trying to reduce number of constants in our code base, number of hard-coded stuff, etc., and config helps a lot in that. And we are utilizing built-in Python library called PyDoc. So PyDoc allows you to import the classes using the names and provide parameters to these classes. So on the right part of the screen, you can see a piece of the actual config that we're using for training, a specified optimizer that we're using, information about loss, metrics, etc., etc. So if I want to, let's say, change optimizer from Adam to stochastic gradient, I need to change on the single line here, name of the optimizer, and rerun my code. Everything will work. So we run offline experiments, collect metrics during training and during test, as I described earlier, using data from staging. So we look both at model during training. Sometimes it gives us valuable insights, and metrics from staging as well, using recall and realized expected value. So if metrics are good enough, we continue with finalizing tests and preparing the pull request. So we have 2 ways of doing tests. First one is unit test, where we're just testing our building blocks. So as I mentioned, we're in config files. In config files, we specify parameters of the blocks that we're using in the pipeline, and every building block should be tested. So the output should be exactly the same as we expected given the input. And the second set of tests is so-called affected tests. So there are a lot of people who are working in the same repository, and we want to be sure that our changes, our new features, won't affect developers in the repository. We're using this blocks structure, so it helps a lot, but still it does not guarantee that others are not affected. So we're running affected tests to ensure that. How does it work? At the same time, we start training using 2 Docker containers. First one built from master branch, second one is built from current branch. We are training it using the same path to the config, using a sample of data for a few epochs. And we check if the input processed data before after model predictions, before after model is trained, model weights before after are the same. So everything is the same, everything is equal. And if it is the case, if everything is equal, we can say that the model is not affected. And indeed, in some cases, let's say when we are doing refactoring, none of your models should be affected. When you are developing one model, other models should not be affected. So this test helps us to find it out. Of course, it's not very sensitive, so we're losing a lot of information. For example, if the effect revealed only after a lot of epochs, or if we need to use larger data set, the effect can be visible, but it's still better than nothing. So we are doing refactoring and we're developing our models with much larger, much higher confidence than before. So we prepare a test, we run them, test pass, we prepare pull request, ask for review. After review, we run an A/B test. So if the model is new and we haven't run similar models before, we assume that it's too risky to run a normal A/B test. So we start with a smaller, shorter A/B test. And in this A/B test, we are looking for dramatic changes such as 2-5% in main metrics. And we are using very small percentage of traffic in this A/B test. So it's not that risky to run this A/B test. So when this A/B test is concluded, when we don't observe significant difference, giving the expected difference in the A/B groups, so if we don't observe, let's say, 5% difference, we assume that the difference is actually lower, and we run a normal test using as many groups as we need on the test, giving the difference we want to significantly observe. And it saves us from running too risky A/B test and sleeping bad during the night. So after A/B test is run, we conclude results of A/B test to discuss next steps within the team. If A/B test is positive, we merge the changes and look after the changes for some time. So we are applying negative test for that. So as I mentioned before, for a small percentage of traffic, we are not using a pre-filtering model. So we send all possible campaigns for the final evaluation to the conversion prediction model. And this test is used both for training our models to avoid feedback loops and biases in our data. And also it's used for running this negative test in which we compare performance of the part of the system without pre-filtering with the system where we apply this pre-filtering. And the idea is that if the pre-filtering model for whatever reason degrades, without negative test, it simply is not observable. And we are blind to such degradation. With negative test, it's much easier to observe such problems. So yeah, that's how we develop our models. So yeah, I think that's it from my side. So here I present the 2 links to this presentation, in case you're interested in looking through them. And also we are hiring. So if you want to join our team of professionals, feel free to reach me out. I post a link to my LinkedIn page in the second slide of the presentation. So that's it. Thank you and take care. Bye-bye.